I'd like to welcome everyone to our presentation on improving color space conversion for camera captured images via wide-gamut metadata. I'm Michael Brown, and I'm presenting this on behalf of my co-authors Hoang and Mahmoud Afifi. We're from York University in Toronto, Canada. And if you're watching the pre-recorded video, I apologize. It means we must be having technical issues with our live presentation. So when you capture an image on your camera, it's capable of outputting the image into several different color spaces. And right now in the industry, there's really three dominant color spaces that are being used by cameras: sRGB, Adobe RGB, and Apple's new Display P3. And some cameras, especially DSLRs, they'll let you select between sRGB and maybe Adobe RGB. Now, what's the implications of choosing one color space over another? There's several pros and cons, but the one we want to focus on is in terms of the gamut. So Adobe RGB and Display P3 are medium-sized gamuts. They can represent about 50% of the visible colors, where sRGB is a well-known small color gamut, and it was proposed many years ago in the early 90s for monitors at that time. Interestingly, we're still dominated by sRGB. So right now, the dominant output on most cameras is this small gamut. Now, one challenging problem is when you want to convert that sRGB image into another color space that has a wider gamut. So let's say that you're using Adobe Photoshop and you want to be able to edit in Adobe RGB, or you're trying to display your image and your display is capable of a wider gamut than sRGB. So we have a mismatch between our color gamuts, right? sRGB is small, these other gamuts are medium sized, so you have to do something to kind of expand that gamut. And you kind of blindly do this because you don't know what those values really should be. There's a lot of related work on this. I can't do justice to everything that's been done before. Very nice work just looking at gamut mapping in general. There's some nice work discussing what would be a better wide gamut color space to use for encoding images. And our work's mostly related to gamut expansion because we're going to focus mainly on how to go from the small gamut, sRGB, to these medium-sized gamuts. And this is challenging because you're given an input image that's a small gamut. You're trying to target a larger gamut. And let's assume that we actually knew what the larger gamut was. So let's just say that somehow I had the ground truth for what these color values should be in our target medium-sized gamut. So, given the image, you try to convert it. If you don't really do anything, if you just do sort of a direct conversion and just keep the colors as they are, you won't be exploding the full size of the output gamut or the target gamut, and so your image can look a little bit dull. But if you just do an expansion and kind of blindly, it may make the image look more vivid, but it could make it look artificial. It could introduce color changes that you don't want, and it could make the image look a little bit oversaturated. So we're going to try to address this problem, and we have one key insight that really helps us improve on what we can do. And in particular, we're looking at the camera imaging pipeline. How does the camera at capture time handle the colors, in particular these different color spaces? And so what I'm showing you here on the screen is a standard camera imaging pipeline where we're modifying the raw sensor input image through all the different stages on the camera pipeline, like lens correction, demosaicing, noise reduction, color space transform into a perceptual color space, photo finishing, and then saving it to the output color space. So if we were to look in the camera imaging pipeline, one of the things that we will notice is that we fairly early in the pipeline convert the raw RGB image, our sensor image, into a wide gamut color space, in particular into the Pro Photo color space. So this is quite interesting. This means we have an internal image state that's already wide gamut. Now after we convert into the wide gamut Pro Photo color space, we will apply our photo finishing. So we do all the sort of photo processing to make the image look good. And then we convert into our output color space like sRGB, Adobe RGB, or Display P3. And one reason we do this at the end is that's what allows us to select on our camera what we want, right? So this is just simply, if you change your setting on your camera, you're just changing the final conversion at the end. So this modular design can be used to our advantage. And our insight really is that we have this wide gamut color samples available at imaging time. So our proposed method is going to leverage this wide gamut ProPhoto RGB values, and it requires us to extract a small amount of data from this ProPhoto image and embed it in our final output image. And I'm going to show you that if we do this, it's going to allow for more accurate recovery of wide gamut color values. So let's just see what we do. So at capture time, we have our raw sensor image. It runs through the camera processing pipeline, but we're going to extract a very small set of samples from the available ProPhoto colors. So I'm showing it here to you. Let me see if my mouse works. I'm showing it here so you can see we just subsample this image, very small, like 150 by 150 color samples. And we're going to embed that inside your output image. And we embed this as a JPEG comment. And without any compression, this is going to take up about 90 kilobytes of additional data. And you could probably get away with even a little bit smaller subsampling here. So pretty minimum overhead for this additional metadata. Now, in my presentation, I'm going to assume the output is always sRGB, but I do want to note that this method can work with any output color space. This is just simply stored as a comment. It doesn't really matter what your output color space is, but we will focus on output color spaces that are sRGB. Now again, where do we get these samples from? So remember, in the camera processing pipeline, we converted into the wide gamut ProPhoto. We did our color processing, our photo finishing, and right before we do the conversion to our final color space, we're going to extract these samples. So this is where we get the samples, right here. Now how do we use them? Well, let's assume that I have, again, an sRGB output image, so I'm in a small gamut image, but I have this additional metadata. So I can extract this metadata. Now from the ProPhoto wide gamut metadata, it's pretty easy for me to convert them into these other target color spaces. So again, if you just look, I know the equations, and if there's lookup tables, I can apply that to go from ProPhoto into, let's say, Adobe RGB or Display P3. These are the two kind of standard medium gamut color spaces we use for cameras. So I can take my extracted metadata, convert it to my target color spaces, and I can take my full-size image, the sRGB image, and I can subsample it to match the size of these samples. So now I have correspondence between my sRGB image and my two target color spaces. And based on that, we can compute a color mapping function that maps these samples from sRGB to Adobe RGB, or we can map from sRGB to Display P3. Now, the color mapping functions are computed on these small set of subsample images, but it turns out that that works really well for processing the full-size image. So I can take this color mapping function that I computed with those small set of samples, but apply it to my full-size image to get the output images that are now in Display P3 or Adobe RGB. Now, when I compute my color mapping functions, I have a couple options. One color mapping function could be a global mapping function. So if I have my sRGB image, and remember we have our target image, which is computed from those ProPhoto metadata, we've either converted to Display P3 or Adobe RGB. Now I can compute a polynomial mapping function that converts this image into this image. And Graham Finlayson has a very nice paper that talks about many different options you have with these type of color mapping functions. You can also do a local color mapping function, so you need to look at the paper for the full details, but all we're doing is we're breaking the image up into small regions, and we're just locally weighting these regions more than the global or all the pixels, so you get a subset or a series of mapping functions for a small region, and so then when you do the mapping, it kind of spatially weights the local region. So it's just a local weighting of the color mapping function. So how well does this work? Well, it works surprisingly well, right? Because we have sort of known target wide gamut values embedded in our image, we can use this when we do the color space conversion. So we're going to show results mainly, exclusively comparing against how Photoshop handles this. So we take our sRGB image, we have the ground truth that we've computed in display P3. So this is our target. We know what these values should be. Now let's look to see what Photoshop would do. So Photoshop would take the sRGB image. I believe we're using the perceptual rendering intent for Photoshop, and it converts it into display P3. We can apply our global mapping, and you can see that reduces some of the color errors, but if we apply our local mapping, we can reduce it even more. Now, I want everyone just to remind everybody, your monitor, I'm sure, is expecting, and I know Photoshop or PowerPoint that I'm using is expecting my data to be encoded into sRGB. So you kind of have to take a little bit of a grain of salt when these images are encoded into these different color spaces. It's just an encoding. My PowerPoint's still showing this to you as sRGB. So we kind of have to look at these error maps to see the difference visually. Just showing some more results. So you can see kind of across the board this works well. So we took images from the NUS8 data set that's used for white balancing. We took the raw images, we rendered them through to sRGB and display P3, and we can show that we can beat things like Adobe Photoshop in terms of overall delta E color. So you can see our local mapping gets much better results. Here I'm just zooming up an image so you can see this sort of color conversion a little bit better. Here's another example. So you can see by using our local mapping with the metadata, we get almost a 50% reduction in errors that we would have using sort of standard methods. Now that was to display P3. It works just as well for Adobe RGB. So we get a very similar trend. So these images were converted into sRGB as well as Adobe RGB. And we can see this would be a standard conversion from Photoshop converting from sRGB into Adobe RGB versus our results using our local mapping. So once again, we get about 50% reduction in error. And I'm just zooming up a little bit here so you can see it. Here's another result. And no presentation would be complete without a giant table of bold numbers. And again, this was the aggregate numbers over 100 testing images. We took these from the NUS8 data set that has very colorful images. We're showing you the mean results, and we're also showing the quantiles, the first quantile, second, and third. So this one's the median values. And we do this for a wide range of different metrics. So two different delta E's. We look at mean angular error and also even peak signal to noise ratio. And you can see in all cases, the local mapping outperforms traditional methods. Okay, to summarize, we presented a method to address gamut mismatch and color space conversion, and namely we looked at how to go from sRGB to median gamut color spaces display P3 in Adobe RGB. Our approach leverages Wide-Gamut ProPhoto data that's available in the camera pipeline at capture time. We extract this and we embed a small amount of this Wide-Gamut ProPhoto color data inside our saved images. And from these ProPhoto samples, we can compute color mapping functions, both global or local, that can aid in the color space conversion, and we show the type of improvements that can be made with that strategy. So thank you for attending, and hopefully we'll be able to answer questions in this online format, and it's really a pity we can't be together. So hopefully next year we'll be able to meet up in Japan.